Biot and Sard law. As we have studied the Oersted law, when the current passes through a conductor, then magnetic field is produced. Now we have to find the how much amount of the magnetic field is produced. Suppose this is the current carrying wire. Current is passing, I current is passing through it, and we want to find the magnetic field at point P. Then, as we have earlier, if the current is increased, then the deflection increases, means magnetic field increase. So the magnetic field here, we take a small portion of this here. Suppose dl is the small portion, we take it. This is the center, and at this point we have to find the magnetic field. This point is at a distance r from this. If theta is this angle between this current and or dl direction and p, then the magnetic field dB at this point P will have a direction. We can give by the right hand thumb rule. This is the direction of current, so magnetic field will be downward. So at this point, magnetic field, the direction of magnetic field will be downward. So we want to find the magnetic field due to this conductor. So we can divide this conductor in different small segments dl. The direction of magnetic field this side will be always the same direction, which is perpendicular to the board inside the board. So we can add it. There is no problem. So the magnetic field dB will be proportional to I. As I increases, dB increases, as I explained the server in the Oersted term. Now second thing, we take the small dl distance, then dB is proportional to dl. So what is the current? Current is the number of charges flowing per second. So if the number of charges flowing per second will be more, then the magnetic field will be more. Now if we take the dl is the small segment of this, and if the small segment is more, then number of electrons flowing in this segment will be more. If it is still more in length, then number of charges flowing per second in this area will be more. In this length, will be more. So the magnetic field will be more. So magnetic field will depend, number one, on the dl length. Number two, it depends upon the current passing through it. Number three, I have in the Oersted law we say that when the current is passing, and if the distance between the magnetic needle and the current carrying wire is more, then magnetic field is decreasing. So here, similar to the electrical field, magnetic field also obey inverse square law. Means the magnetic field will be inversely proportional to r square. So magnetic field will be proportional to 1 by r square. Now third thing is that magnetic field also depends upon the direction or the angle between OP direction and current direction. We can say this angle or this, it makes no difference, because if it is theta, then it is equal to 180 minus theta. So sin theta will be equal to sin 80 minus theta. So we can take either this angle or this angle. Then dB is also proportional to the sin theta. So sin theta is the angle between this element dl and r. So if we combine these all the factors, then the magnitude of dB will be some constant into I proportional to Ia, proportional to dl, proportional to sin theta, and proportional to 1 by r square. So dB, magnitude of dB will be equal to C multiplied by I into dl into sin theta by r square. Now proportionality constant C is equal to mu by 4 pi, and its value is 10 raised to minus 7 Tesla into meter into ampere inverse. So now here what is mu 0? Mu 0 is the permeability of the magnetic field in the medium, and when it is 0 means it is a free medium. So it is mu 0 is the permeability of free space or permeability of vacuum. So what will be the unit of mu? The unit of mu will be also equal to P into m bata A. यहाँ क्या आपका P into m bata A, and or it is Newton bata ampere square, or it is Weber bata ampere square. So these all are equivalent. And what will be the dimension? We put any dimension. We take the Newton, then MLT minus 2. Here current is ampere square. So the dimension of mu 0 will be equal to MLT minus 2 into A minus 2. So this will be the dimension of permeability of the medium. Now, beyond Sadler, what if the theta is equal to 0? Sin 0 is equal to 0. So dB is equal to 0. Means if we take the magnetic field in this direction, which is in the direction of current, it will be always equal to 0. Then second, when theta is equal to 90, when this angle is 90, sin 90 is maximum 1. So the dB will be maximum when theta is equal to 90. So if we take, then what will be dB? dB will be equal to mu 0 bata 4 pi I dl bata r square. So if the current is 1 ampere, the length of this wire is 1 meter, and distance from the center of this to this is 1 meter, then dB will be equal to mu 0 bata 4 pi, or mu 0 bata 4 pi is equal to 10 raised to minus 7. So the magnetic field will be equal to 10 raised to minus 7 Tesla. So if the length of the conductor is 1 meter, the current passing through is 1 ampere, and distance from the conductor is 1 meter, then the magnetic field produced will be equal to 10 raised to minus 7 Tesla. So we have a magnetic field and we have an electrical field, and in the electrical field and magnetic field we can write electrical field dE is equal to 1 bata 4 pi epsilon 0 Q divided by R square, and dB is equal to mu 0 bata 4 pi I dl sin theta bata R square. So what is the comparison? This is from the Coulomb's law and this is from the Boyle-Short law. So what are the similarities between the Boyle's law and Coulomb's law? Number one, here both are obeying the inverse square law. dB is proportional to 1 bata R and D is proportional. So inverse square law is applicable for both each other. Now electrical field and magnetic field both are vector. So the superposition principle will be applicable for electrical field as well as the magnetic field. The range for electrical field is infinite. Similarly, range for the magnetic field is also infinite. So these are the similarities. Number one, it is proportional to 1 bata R square. Number two, both are the vector quantity. Then the range for both is infinite. So since when both are the vector quantity, then the superposition of vector will be applicable for magnetic field as well as for the electrical field. Now what are the dissimilarity? Now dissimilarity is Here Q is a scalar quantity. Here I into dl is a vector quantity. IDL means ideal we can also say this is the current element. It is a vector quantity. Whereas Q is scalar quantity. Now the direction of D is in the direction of R. Whereas the magnetic field is perpendicular to R. The magnetic field is perpendicular in the board, so it is perpendicular to R, whereas electrical field is in the direction of R. Now, electrical field doesn't depend upon theta, whereas magnetic field, with Bayes' law, it depends upon theta, sin theta is there. So, these are the differences. Here also one more difference we can say. Here it is equal to mu 0 bata 4 pi. So here, if mu 0 increases, if permeability increases, B increases. Here, permittivity increases, then electrical field decreases. So this is the difference. Here, permittivity will increase, then force will be, or electrical field will be less. Here, when the permeability is more, then magnetic field is more. So these are some similarities and dissimilarities, or we can compare Bayes' law and Coulomb's law by this point. So the application of Bayes' law. The magnetic field due to state conductor of finite length. So this is a conductor whose length is xy is conductor, length is finite, I current is passing through it, and we have to find the magnetic field at point P. So we drop a perpendicular here on the xy line, and this is suppose at the point A. We join P and Y and P and X, and the angle Y P X is equal to phi 1. Angle A P X is equal to phi 2. So if we take any point here, B point here, and this distance is L, AB is equal to capital L or small l, the distance, and here we take a small element dl, and from the center of this dl, this distance is small r. Here AP is capital R. Capital R is the perpendicular distance from P on this straight wire, and here this angle is beta, and this distance dl and P, that is BP, that is smaller. So here AB is small l, APB angle, here the angle subtended by this AB, if this angle is suppose beta, AB is equal to R, OP, this is BP, BP is equal to small r. Now from the Bayes' law, the magnitude of magnetic field due to this small dl at this point will be equal to mu 0 bata 4 pi I dl sin theta bata r square. Now we will change dl sin theta and r in terms of capital R and angle theta, phi and phi 1 and beta. So first of all, then we take this angle is theta. Theta is angle between this small dl and current. So this theta will be equal to this angle is perpendicular. So this angle is 90. So beta will be equal to this angle is 90. So angle theta will be equal to 90 minus p. So sin theta will be equal to sin 90 minus beta, which is equal to cos of beta. So this is equation number 2. Now here we take angle APB. then tan beta will be equal to perpendicular beta base. So it is L beta R. So L beta. So small l will be equal to R tan beta. We differentiate it. Then dl will be equal to R sec square beta into d beta. Equation number 3. So here we have a relation to sin theta. Here d theta. Now we will relate small r. Now from this angle, what is the cos theta? Cos beta will be equal to base beta hypotenuse. So in APB triangle, cos beta will be equal to AP beta BP, and AP is your R divided by small r. So small r will be equal to capital R beta cos theta or capital R sec theta. Now we substitute value of dl sin theta and r square from this equation, in this equation from 2, 3 and 4. So d beta will become mu zeta 4 by I will be same, and dl is equal to I sec square theta beta into d beta into cos beta divided by r square. This is r square, so r square sec square theta. So sec square will cancel, 1 r will cancel. So dv will be equal to mu 0 beta 4 pi I cos beta d beta beta r. Now this is for the small. So if we want to find the total magnetic field for the entire xy wire, then we have to integrate it. If we take any small element, then the direction of magnetic field will be always downward. That will be same, and it will be perpendicular to the board inside it. So we can integrate and find the value of. So here angle APX is phi 2, APY is phi 1. So here we integrate it. So integrate it, then dB will be equal to B will be equal to mu 0 beta 4 pi. I is constant, R is constant. So integral, then inside is cos beta d beta, cos beta d beta. Now angle, here angle will change from, this is minus because it is in the clockwise direction. So it is positive, negative, and this is anti-clockwise, it is positive. So phi 1 is positive, so minus phi 2. So the d phi will change from minus phi by 2 to phi. So here the limit will be minus phi 2 to phi. Cos beta d beta. So cos beta integration will be sin beta. Then so it will be equal to mu 0 beta 4 pi I dl sin theta 1 sin phi 1 minus sin of minus phi 2. So it will be plus phi 2. So it will be equal to sin phi 1 plus sin phi 2. So the magnetic field due to this will be equal to mu 0 beta 4 pi into I divided by R multiplied by cos phi 1 and cos. If the length of this wire is infinite, infinite means if it is an infinite, so if we take point P is very close to it, then this angle and this angle will be equal to, this will be plus pi by, this is pi by 2, this is also pi by 2. This angle will be, when it is very light, it will be pi by 2, it will be pi by 2. So the magnetic field, when the conductor is infinite length, then it will be equal to mu 0 beta 4 pi I to R. R is this distance. R distance will be very, very smaller than the length. So it is very close, so it will be equal to pi by 2 and pi by 2, sin pi by 2 and sin pi by 2, 1 plus 1, 2. So it will be equal to, B will be equal to mu 0 beta 4 pi 2I divided by R. So this will be the magnetic field. If the conductor is of infinite length, and this is the condition when the conductor is of the finite length. So in this way, using the Bio and Savart law, we can find the magnetic field of a straight line conductor of definite length or infinite length.